Hello everyone, I welcome you all in this lecture. So in this lecture, we will cover the aircraft longitudinal dynamics part and we will continue from the previous lecture. So as I promised, today we will cover the aircraft mod, how to obtain, how to analyze, how to get the information from the aircraft longitudinal mod in order to comment on a aircraft dynamic stability. Here in this case longitudinal dynamic stability. Okay, so first we will take in a physical aircraft. Here in this case we will take a motor glider. In this lecture we will cover the linearization. We will linearize the aircraft dynamics, since in order to find the mod you have to decouple, and if you want to decouple you have to linearize. So in this we will cover the technique, equilibrium points and longitudinal dynamics, and then we will move to the aircraft mod and we will find out the aircraft mod and we will analyze in a longitudinal case. So basically in longitudinal case we will be having two mods, one is short period mod and other one is a Phugoid or long period mod. We will cover in detail. So you can see this is a typical view of a aircraft which we have considered for a aircraft longitudinal mod. This is a motor glider. If you type sinus glider in a Google, you will get all the information. Okay. So as we all know, the aircraft equation of motion is first order ordinary differential equation. We have covered in detail in the flight control system design course. You can go there and see the lectures, and also you can see how I have simulated this equation of motion in a system dynamics and MATLAB course. Okay, aircraft physics of simulation also I have covered in that course, so you can go and check. Okay, so the same aircraft dynamical equation we will take and we will linearize using Taylor series. We will take only up to first order term, and this will be our linearized equation. Okay, so this is the way you can find out the Jacobian. For example, instead of in a generic case the equation is written x dot equal to f plus gu, where f and g are non-linear functions. So we have to linearize using Taylor series, and after linearizing you can write actually h dot equal to ax plus bu, where a is a system matrix, b and a control matrix after the linearization, and a and b is independent of a time. Okay, so you can this is how you can find out the Jacobian. You can see in a first row the u dot is differentiated with the longitudinal aircraft states u, w, q, theta, h. Similarly w dot and q dot, theta dot and h dot. Okay, here u, w, q, theta, h are the longitudinal states. So you can see here we are having 5 cross 5 matrix, system matrix. Similarly, the control matrix can be obtained by differentiating with respect to the delta E and delta T, because delta E and delta T are the longitudinal controls. Delta is elevator, delta T is a throttle. Okay, so you can see here 5 cross 2 is a control matrix, right? So once you do this, and then you can find in a system matrix A, you can find out the characteristics equation, which is nothing but the lambda I minus a determinant. Okay, so here if you take a, I mean to say, if you remove that H part, you can consider only U states, W states, and theta and Q. You will find out the you will be end up with the 4 cross 4 matrix, and here you will find the two roots, lambda and lambda 1 and lambda 2. So you will see that typical the root will look like this. One root will be close to the origin and one root will be far from the origin. Okay, the root which is closest to the origin you will say as a Phugoid mode, and the root which is little far or far away from the origin will be called as a short period mode. Okay, see, we know that if root is far from the origin, that means omega is more, frequency is more, damping is more. So then you can say that this root will be having more frequency, more damping ratio, this term as a short period mode. fast damping, okay, highly damped, okay, and which is close to the origin will have a oscillatory nature, okay. I mean to say, if it is closest, if it is having imaginary part also. So here you have a less negative real part, that means it will take a more time to damp out, okay. And if it is, so here based on the root location you can actually comment on which one is my short period mode and which one is a Phugoid mode. So in a short period mode generally V is constant, because the moment the short mode is activated is suddenly damped out, so velocity does not have sufficient time to change because it's slow variable than compared to the pitch rate and all, okay. Whereas in a long period mode it has a less damping, so it will take more time to damp out. So you can see here the angle of attack is constant, okay, and altitude is changing and angle of attack constant, but here velocity is constant and angle of attack is quickly damped out, you can say, okay. So this way you can differentiate the short period mode and long period mode, okay. So this you can locate on a root locus. So root locus part already I explained to you. If you have a roots, then you can actually place this root on a root locus. So how to draw the root locus I have already explained in the system dynamics and control using MATLAB and Simulink course. You can go there and you can understand how I explain the root locus. All right, okay. So here you can actually place the root locus and you can actually move this root, and you can do to check different damping. For example, like if you don't satisfied with the natural damping, you can actually take a feedback of a Q in a control system design course. Already I explained that, and you can manipulate the damping. This is the advantage of root locus, okay, to select the appropriate damping, okay. Naturally aircraft will have some damping. So when we are talking about the aircraft dynamic stability, we are dealing with the natural response only, okay. Okay, so here damping ratio, natural frequency, root, and time to half and time to double you can find out. Now the question is, what do you mean by time to half and time to double? Okay, so here you can see that in this diagram, in A diagram, the system is disturbed or aircraft is disturbed from the equilibrium position, and it is taking time to damp. Okay, so you can slowly it is or fast is depending is damping out depending upon the damping. Okay, in the second case it is a diverging, but the unstable case. Okay, so when you may say time to half, that means you are talking about the dynamically stable aircraft, and when you are saying time to double, then you are saying about, you mean dynamically unstable case, because amplitude is increasing, right? So that is why it is not half, it is double. Okay, so let's say for example amplitude is x, so how much time it will take to become x by 2, that is called time to half. And when it is x, then how much time it will take to become a 2x, that is called time to double. So time to the double refers to the unstable case, and time to half refers to the stable case. So already we know the solution x equal to x naught e to the power minus lambda t. Since this is a stable case, so lambda is negative. Okay, so put x equal to x by 2. Okay, and find out the time. You will get 0.693, which is nothing but the log 2 divided by lambda. And for example, like if you want to find out the number of cycles, how much cycles it will take to to, to half its amplitude, then you can find out omega into t equal to 2 pi n. So number of cycle for a half or double, it will be 0.11 mod omega by n. Okay, so again I am saying, if you are referring to the stable system, time to half, number of cycle to half will come into the picture, and when you are referring with the unstable system, then time to double and number of cycle to double the amplitude will be there. Okay, next question. This is all about the longitudinal aircraft dynamic stability part. If you have any question related to short period mode, related to Phugoid mode, related to what aircraft I have considered, and what is the typical value of time to double, time to half, these things, anything related question for a different aircraft, You can post this in a comment section. I will be happy to answer. Okay. And you try a different aircraft and apply this technique and try to have a feel for a route location, natural frequency, damping ratio, okay, and time to half, time to double. Okay, for example, let's say this motor glider is a for a very long span, more than 15 meter. Okay, and as per the ratio is close to 20. Okay, so this kind of aircraft can, in this case, the LBID is very very high. I mean to say more than 15, you can say. So in this case, if you roughly estimate the zeta, so that will be 1 divided by under root 2, okay, into 1 divided by L by D. So you will get a feel for roughly zeta value. So you will observe that in this kind of aircraft you can easily achieve the long period mode, because zeta is inversely proportional to L by D. If you increase L by D, zeta will decrease. So that is why in a glider case you can easily activate the Phugoid mode, but but in a case of fighter aircraft it will be difficult to activate the Phugoid mode. So this kind of feeling actually you can take. And when you consider the motor glider type, you will see the time to half its amplitude is long. For example, more than 20 second, 30 second. Okay, if you have any question, I will be happy to answer. Thank you so much.